Hey there, I'm Nix, and the topic of today's video is solving array partition 1 on the LeetCode website. As always, we're solving this in the C++ language, and I'm giving you a detailed explanation of the entire process, through the planning of the algorithm, to the coding of it, to the analysis of its time and space complexities, as well as looking at LeetCode rankings. If that sounds interesting to you, then stay tuned. Welcome back, and let's get to it. So we are given an integer array, nums, that consists of 2 n integers, and we want to group these integers into n pairs. So for example, if we are given an array with 10 numbers, we want to have 5 pairs. We want to do that in such a way that the sum of the minimum of the pair for all I is maximized. Return the maximized sum afterward. So we're going to have a variable that is going to hold this maximized sum. Now let's look at this example here and analyze it to make sure we thoroughly understand the problem and start planning out how to attack it. So we have an array that consists of 4 numbers, 1, 4, 3, 2. And our output that's desired comes out to be 4. Well, how did they get that? Well, since we have 4 numbers in the array, we want to group them into 2 pairs. But how do we do that in such a way that the smaller of the numbers in each pair, when added together, gives us the biggest number? Well, we could pair up 1 and 4 and 3 and 2, like we see here in scenario 1. And then the smaller of the 1, 4 pair is 1, smaller of the 3, 2 pair is 2, so 1 plus 2, when you add them together, 3. We could also pair 1 with 3 instead, and then that means the 2 even numbers get paired together. But that still equates to a minimum of 1 for the first pair and a minimum of 2 for the second pair, so it gives us the exact same thing. However, pairing 1 and 2 and then 3 and 4 together means that our first minimum pair still has 1 as our answer, but the 3, 4 pair now has 3 as our minimum, and 3 plus 1 equals 4, which is how they get that. Now looking at this problem, we can see that, say, take this 4 here. That 4, no matter what it's paired with, is always going to be a maximum because it's the highest value present in the array. And with that quality, it has a special superpower. Whatever it's paired with is automatically going to be the minimum of the pair, and thus that number is going to be counted. So in order to maximize our count, the best number to pair with it would be, say, if this is the maximum, pair it with the second highest number in the array. On the opposite end here, 1, the lowest value in the array, is going to be a minimum no matter what it's paired with. It's always going to be counted. So the best thing to do for its pairing is to pair it with the second lowest value. Because as we see here, pairing it with 1 and 4 and 1 and 3 just mean that 3 ends up being counted as a maximum in those pairs, and we lose out on 1 additional value. And that brings us to the first characteristic to key into for this problem, and that the optimal pairing of any array is essentially going to follow their sorted order. 1 with 2, 3 with 4, 5 with 6, so on and so forth. So since this array that we're given is not guaranteed to be sorted, well, a good first step would be to sort it. Now that we're dealing with a sorted array, we know where all of the minimums are and all of the maximums are. As we see here, when we sort this array, we get the pattern of minimum, maximum, minimum, maximum. All of the minimums are going to appear at the even indexes. So if we go through the sorted array now and add up all of the values that are present at those even indexes, then that is all we need to do in order to get our answer. That also works in this example here, which you can see the sorted version of the array on my handy dandy whiteboard. Here are the 3 pairs that we end up with, And we can see that the minimum of each pair occurs at index 0, at index 2, and index 4. And of course, when we add 6 plus 2 plus 1 up, we get the expected output 9. Going over all of that, let's code that out and see how it performs. First up, the only variable we need here will be to house the maximum sum, and I've set that to 0 initially. Next up is to sort the array that we're given, nums. And the most efficient way to do this is simply by calling the built-in C++ sort function in its library. Sort from the beginning of the nums array to the end of it. Now that our array is sorted, we can start looping through it and adding values up. And this for loop is almost exactly what you would expect for a default one, save for one difference. We still start at an index value of 0 here. We want to go until we reach the end of the array. But the step that we want, the increment, instead of incrementing up by 1, we want to increment up by 2. So we set it to I plus equals 2. This will make sure that we're only looking at the even indexed values. And what we want to do is set the maximum sum equal to itself plus whatever the value that we're looking at via the plus equals operator. Finally, at the end of this for loop, our max sum should house the correct answer for the problem. So all we need to do is return max sum. And with those lines of code, this algorithm is complete. So let's see how it runs and see if we get horrible red text, which we don't. Excellent. And we get the expected answer. Great. And now let's go for the full shebang. Submit to judgment, and we get lovely green text. Wonderful. Now, as always, before we hit the button to see our ranking, let's look at our time and space complexities. For space complexity, the only thing we have in terms of variables here is the integer max sum, which takes up a constant amount of space, and thus our space complexity should be equivalent to big O of 1, constant space usage. Now for time complexity, we need to look at the sort function and the for loop. Now the for loop is going to essentially be dictated by the size of the input array, nums. The bigger the input, the more iterations it's going to take, the longer it's going to take. So that section would be big O of n, where n is equal to the input size. However, sort has a higher time complexity than that. Sort has a big O of n log n, where n again is the input size. So this entire algorithm would technically be big O of n log n plus n. But because of the rules of figuring out time complexity, we only care about the highest order term, which in this case is n log n, so we just kind of forget about the big O of n part. So the answer for the time complexity of this algorithm would be big O of n log n due to the sort function here. With that done, let's go look at our rankings. Okay, pretty much a bell curve-ish looking distribution here. So I'd expect some parts to ping pong around. So it would likely end up probably staying around this zone for the most part. And looking at memory complexity, very, very small range here. So I'd expect more ability to ping pong around this area instead. And of course, if you're curious, you can always click these columns to see other answers. Really good way to learn and sharpen your coding skills to see what neat other solutions other people have come up with. Anyway, that was how to solve the array partition 1 problem on the LeetCode website. I hope you got something out of this video. If you did, consider subscribing. And as always, I will wish you happy coding and to have a nice day.